Okay, this is a lecture that I have just started making part of the astronomy class, and it's usually something I just talk about for a few minutes to make sure everybody gets the general idea of scientific methodology. But the more I think about it, the more I realize this is probably the most important thing you'll learn in this class, is to think critically about what scientific theories are, how the methods of science work, and how you are to think about scientific theory. So I want to spend some time early on in the course talking about how science really works and how it might be a little bit different from some of the pictures of science you were taught in school, and how actual science is actually a little bit more complicated than the kind of cookbook methodology that we learn about in elementary school and middle school and high school. The term that gets tossed around a lot when you're talking about science is the idea of a scientific theory. We will, in this course, talk about all sorts of scientific theories. The Big Bang Theory, the theory of relativity. There are Newtonian theories of gravity. In chemistry, there's atomic theory. In biology, there's the theory of evolution and the germ theory of disease. And the one thing that we should keep in mind whenever we hear someone talking about a scientific theory is that the word theory in science means something very specific, and what it means is actually pretty different from the way that word is used in everyday conversation. The phrase you should banish from your vocabulary entirely is the phrase, "that's just a theory," because it implies that there is something better that you can be in science, and that is not true. A scientific theory, a well-tested, verified, predictive, unifying scientific theory is the best thing that science can produce. There is nothing better in science than a successful scientific theory. So there's no just or no only about it. Scientific theories do not graduate somehow to something better than a theory. Some of the confusion about how this terminology is used comes from the way we use the word theory in everyday life. If you look up theory in the dictionary, you will find definitions like this: a hypothetical set of facts, often used in the phrase, "in theory, such and such," when what you really mean when you say "in theory, such and such" is that such and such is only hypothetical and not true. A hypothesis assumed for the sake of argument or investigation, or an unproven assumption, or a conjecture, or a speculation. None of these things are what the word theory means in the context of science. A scientific theory is a broad, unifying, explanatory framework or model. It is an explanation of why things work the way they do. It's an explanation of our measurements and observations and facts that we have gathered about the world. So science is in the business of producing scientific theories, and a scientific theory is the end point of the scientific process, not the beginning, and not a halfway step towards something like capital T truth, which is a word we have to be very, very careful with when talking about science. So what makes a scientific theory a good scientific theory? It should be simple in that it should not postulate a whole bunch of entities that aren't needed or can't be observed or have no effect on the theory. It should be unifying, meaning it should explain a whole bunch of things, observations, facts, laws, measurements, under one conceptual umbrella. It should be predictive, meaning you should be able to use that scientific theory to make predictions about things that you have not yet observed, and those predictions should be testable. It should make predictions that you can then go out and do additional experiments, perform different additional measurements, additional observations to see if the predictions of that theory are in fact true. You might say, well, what about a fact? Isn't a fact better than a theory? Like, isn't a fact something we know is absolutely true? No. Facts are not better than theories. A fact is the result of a simple observation or experiment. Here are a bunch of facts about astronomy. Betelgeuse is a red giant. That's a fact. The sun's surface has a temperature of a little under 10,000 degrees Fahrenheit. Fact. The Earth's mass is a little less than 6 times 10 to the 24th. Remember your scientific notation. 24 zeros is a trillion, right? 12 plus 12. So the Earth's mass is about 6 trillion kilograms. Fact. The universe is, by mass, 73% hydrogen and 25% helium. Those are all scientific facts. They're the results of observations and measurements. But notice that they, by themselves, don't really tell us anything or even really mean anything that we can draw any conclusions from. Okay? Facts are simply the results of observations, measurements, and calculations. They are not better than theories, and they don't really do anything by themselves. Facts don't even really mean anything until we combine them with other facts. And those facts taken together might mean something if we have a scientific theory that gives them context and connects them to one another. So, for example, the fact Betelgeuse is a red giant. So what? What does that mean? It's red and it's big. Does that tell us anything scientifically? Does that tell us anything about Betelgeuse's history? Does that tell us anything about why it is big and red? Does that tell us anything about why it's different from the sun? No, it doesn't really tell us anything at all. What we need to make sense of that fact is a theory of stellar evolution, which we'll talk about in a couple of weeks, that explains how red giants come about, how they are different from a yellow dwarfish star like our sun, and to put that fact into a bigger picture, a theory that explains the reason why that fact is true and what it means in the context of all the other facts that we know about stars. So theories do not graduate into facts. Theories explain facts. A fact is a piece of a theory, but by itself doesn't really do anything for us or help us scientifically. You might say, okay, what about a law? Laws sound important, right? The law of gravity sounds like something that we absolutely know is true. Maybe. But just like facts, laws don't really explain anything. If we take a look at something like the law of gravitation or the ideal gas law from chemistry or Newton's laws of motion from physics. In this astronomy class, we'll talk about Hubble's law, which is a mathematical relationship between the velocity of the distant galaxies as they expand away from us and how far away they are from us. A law is just a mathematical relationship that relates some physical quantities to one another, at least in physics. In biology, a law might have a slightly different meaning. It's more like a description of a relationship, but it's still not an explanation of anything. It's merely, in the case of physics, a quantitative expression of a relationship between quantities. Here, for example, is Newton's law of gravitation, which we'll see in a couple of weeks. It says the gravitational force between two objects is equal to the mass of one object times the mass of the other object, divided by the distance between them squared, times this number g, which is called Newton's gravitational constant. It doesn't tell us why there's gravity. It doesn't tell us what gravity is. It doesn't tell us what mass is. It just tells us if we have two objects with mass, they will exert a gravitational attraction on one another. It is a simple quantitative relationship between mass, distance, and the force of gravity. Yes, this law is important, but it doesn't actually explain anything. It's just a description of what happens, a quantitative description, an important, useful quantitative description, but not an explanation of what gravity is or why it happens. What that would require is a theory of gravity, which explains what mass is, what forces are, why Newton's gravitational constant has the value it does, what is it about mass that causes gravity? All of these things are part of a broader theory of which this law is just a tiny, tiny piece. So a law is not better than a theory either, because a law does not explain anything. It just expresses a relationship between quantities. So the way we use the word fact and the way we use the word theory in everyday life is very different from the way that they're used in science. When we talk about something as a fact in everyday colloquial English, we mean something that is proven to be true. That is not what fact means in science. When we use the word in theory or theoretical or only a theory in everyday English, we mean something that should be true but isn't, or might be true and we're not sure. That's not the way we use theory in science either. So a good theory, what a good scientific theory does, is to provide an explanation for facts and laws that is unifying and explains them under one conceptual umbrella. Suppose we have three phenomena in nature: phenomena X, phenomena Y, phenomenon Z. What scientists do is we go out and we measure stuff about X, Y, and Z. We might learn a bunch of facts about X, a bunch of facts about Y. We might learn some laws about relationships between X and Y. We might learn a law about phenomena Z. Whatever these phenomena are, they could be anything. They could be molecular forces between atoms. It could be how planets form. It could be how the force of attraction between atoms works. It could be how moving tectonic plates cause earthquakes and volcanoes. Whatever these phenomena are, we gather a bunch of facts by making observations and doing experiments. We create a bunch of laws by observing the quantitative relationship between those two things. Those things aren't explained until we have a framework of a theory to connect them together. For example, I know that the atomic weight of carbon is about 12, and the atomic weight of nitrogen is about 14, and the atomic weight of oxygen is about 16. For a long time, those were just disconnected facts that had nothing to do with one another. The weight of carbon happens to be 12, and the weight of nitrogen happens to be 14, and the weight of oxygen happens to be 18. But when we had a theory of atomic physics and learned about protons and neutrons that make up atomic nuclei, suddenly those facts have an explanation. The atomic weight of carbon is about 12 because it has 6 protons and 6 neutrons. 6 plus 6 is 12. The atomic weight of nitrogen is 14 because it has 7 protons and 7 neutrons. The atomic weight of oxygen is about 16 because it has 8 and 8. 8 plus 8 is 16. So the theory of atomic structure and nuclear structure explains why the atomic weights of carbon, nitrogen, and oxygen are 12, 14, and 16, and it connects those facts together in a way that weren't connected before. We might have one theory about certain phenomena and a different theory about different phenomena that are disconnected from one another until some point in time where someone comes up with a bigger theory that connects all of those facts together. That is an important thing that happens in science called unification. A moment of unification is when some things were thought to be separate phenomena. A new theory shows that, hey, these things are actually the same phenomena after all. I'll give you one important example from the history of physics and astronomy. Before Isaac Newton, if you asked the question, why does this rock fall when I drop it? And you asked the question, why does the moon go around the earth? Those were considered to be completely different things. One is about what happens here on earth. Water and rocks fall to the ground. And the other is about what happens in space. Things in space move in circles. Before 1687, nobody would have thought that those facts were related to one another until Isaac Newton came along in 1687 and said, there is an attractive force between all massive objects, and the force that attracts a rock to the earth is the same force that holds planets in orbit around the sun, and the moon in orbit around the earth, and Jupiter's moons in orbit around Jupiter. The theory of gravitation of Isaac Newton is important historically because it represents a moment of unification. When Newton came up with one theory that explained one set of facts about what rocks and water and things on the earth do, and another set of facts about what Jupiter's moons and Saturn and Mars and Venus do, under a single theory, which is the theory of gravitation. We will see later on in the course examples of unifications that are incomplete, and the fact that, in physics anyway, the goal of unification is actually very often a driving force which causes us to refine our scientific theories and try to make them better by making them more unified, by making them explain more things under one conceptual model. If you want to take a break, now would be a good time to pause and think about the way you use the word fact and theory in science. I want to do a little bit more before I wrap up this video. I could stop and make a separate video, but I think I want to just keep going here. I think we'll still be around 25 minutes when I finish. And I want to talk about I almost called it a lie, but the simplification, the cartoon that we teach you in elementary school and middle school that we call the scientific method. The reason it's a cartoon is there is no one scientific method, and the idea that scientists go to work in the morning and they pick which of these steps in the scientific method they're going to do today is silly and wrong and not how science works at all. There are some scientists that all they do all day long is they run experiments. There are scientists who all they do all day long is come up with scientific theories. So one thing to keep in mind is that no one scientist is ever enacting all of the steps of the scientific method. In fact, the theories that we're testing may be theories that somebody came up with before we were born. But the other thing I'm going to talk about that's a little bit naive about this picture is this notion that, again, we're taught this in school, that you have a hypothesis that comes from your theory, you do an experiment to test that hypothesis. You do an analysis to see if the hypothesis and the results of your experiment match, and then you draw a conclusion about whether or not your hypothesis was correct. And the question is, what do you do after you draw the conclusion? The naive picture that we're sometimes taught in school is that if your conclusion doesn't agree with your hypothesis, you go back and you change your scientific theory. Okay, you throw away your hypothesis and you come up with a new scientific theory to explain the results of your experiment. And that picture is oversimplified. And I want to talk about the oversimplification right now for a little bit. So one place where this kind of cartoonish middle school classroom poster version of how science works fails is the implication that what we do when we have an unexpected result is to immediately toss out our theory and start all over again. And I want to give you an example of why this is kind of naive and not really the way science works from the history of astronomy. The planet, we talked about the fact that when you look up in the sky with your eyeballs, you can see Mercury and Venus, and you can see Mars, and you can see Jupiter and Saturn, and that's it. 5 planets. If you add the Earth, that makes 6 planets that, say, Isaac Newton knew about in the 1600s. Uranus, Neptune, Pluto, minor planets and asteroids and stuff, you need a telescope to see them. William Herschel, a British astronomer, discovered the planet Uranus in 1781 just by accident, just from poking around in the sky with his very big, powerful telescope. Once Uranus was discovered, and once we realized, hey, this thing moves every night and it is a planet, we decided to use our law of gravitation, which is Newton's law of gravitation, which we saw a few minutes ago. If we know how far Uranus is from the sun, we know the gravitational force that the sun is exerting on it. We should be able to predict then how it will move through space using Newton's law of gravitation. So we can use our existing theory, Newtonian gravity, to predict where Uranus will be in a day, a month, a year, 20 years, whatever. We did that, and using the motion of Uranus through space, we predicted where it should wind up in a day, a month, a year. And those predictions were always, after a little bit of time, off, a little bit wrong. Uranus was never quite where we predicted it to be. In other words, if we look at where Uranus is tonight and predict, all right, according to Newton's law of gravitation, where will it be in 6 months? It was always a little bit off. So what do we do with that? We make a scientific prediction. That prediction is wrong. What does the naive middle school cartoon poster of the scientific method suggest that we should do with that? Well, it suggests that we should revise our prediction. But how do we do that? Do we say, I guess Newtonian gravity is wrong. It worked okay for about 100 years, but I guess we have to throw out all of classical physics invented by Isaac Newton because it doesn't correctly predict where Uranus will be. I can assure you that nobody in the early 1800s suggested that we throw away all of Newtonian physics because Uranus isn't quite where it was predicted to be. What do you do instead? First, you go back and you double check your measurements. You make sure your measurements were accurate. You make sure you took all the parts of your experiment into account. Are we sure that our telescope is pointed in exactly the right place when we measure Uranus? Are we sure that distortions caused by the lens might not have our position of Uranus a little bit off? So we checked those things. Uranus still wasn't quite in the right place. The second thing, though, is we go back and we check all the assumptions that went into our prediction. One of the assumptions that went into the prediction is that the orbit of Uranus is governed by the gravitational pull of the sun and nothing else. But what if that's not true? What if, instead of throwing away our theory that we used to generate our hypothesis, we reanalyze that prediction and say, maybe we missed something when we were making our prediction. Maybe the only force of gravity acting on Uranus is not the sun's gravity, but maybe there's some other gravitational pull pulling on Uranus, something we can't see and we didn't take into account when making our prediction. So we did that. And we said, all right, if we predicted Uranus would be here and instead it's there, where would the thing have to be exerting a gravitational pull on Uranus? And we calculated what direction that gravitational pull would be coming from. And then the person who did the calculating, I think it was Leverrier, the person who did the actual telescopic work, his name is escaping me right now. I wish I had my Alexa here so I could say, Alexa, who discovered Neptune? But the upshot is, we pointed our telescope at that point in space where we thought this gravitational pull should be coming from, and we found a planet there. And that planet is now called Neptune, 1846. So what does that teach us? That teaches us that one of the things you can do when your experiment doesn't quite turn out the way you expected is not to throw out all of your scientific theory. It's go back and to ask yourself, could there be something that we're missing? Could there be some effect or some force or some influence on our experiment that we did not realize was there? That is much more common than taking a scientific theory and throwing it away completely. The idea that the way science works is by completely throwing away any result, or completely throwing away a theory when any result doesn't agree with our predictions, is the reality is much more complicated than that. The reality of how we go about making predictions, testing them, comparing the predictions to reality, and falsifying scientific theories is a complicated process that bears not a whole lot of resemblance to the cartoony version we learned in school. But this idea that what experiments are meant to do is to falsify or disprove scientific theories is an important one in the philosophy of science. This idea that what makes science science is that when we do an experiment, we can disprove our theory, comes from a Austrian-English, born in Austria, later moved to England, scientist named Karl Popper, early 20th century philosopher of science, not a scientist, but a philosopher, whose job it was, and it's the job of philosophers of science, to think about how science actually works and how scientific truths, I'll put that in big scare quotes, because what does that word mean? How they are arrived at and what they mean. Popper's most important work was a book called The Logic of Scientific Discovery, which was originally published in 1934 in German, 1959 in English. And the question Popper was concerned with was not necessarily how science is done, although later a lot of people used Popper's ideas to talk about how science is done. The question that Popper was interested in is what makes science science? What makes an idea a scientific idea as opposed to something else? This is a very wordy description, but I'm going to read the whole thing because it's important. Popper said that I will admit a system as scientific only if it is capable of being tested by experience. So if you can't do an experiment or a measurement to test something, it's not scientific. Furthermore, these considerations suggest that it's not the verifiability, but the falsifiability of a conceptual system that's to be taken as a criterion of demarcation. In other words, how do you demarcate what is science from what is not science? In other words, I shall require not that the scientific system be capable of being singled out once and for all in a positive sense, but I require that its logical form shall be such that it can be singled out by means of empirical tests, experiments, and measurements in a negative sense. In other words, it must be possible for an empirical scientific system to be refuted by experience. It must be falsifiable. In order for a scientific theory to be a scientific theory, according to Karl Popper, and he's not the only philosopher of science, by the way, it must be possible to do an experiment that disagrees with the theory so you can say, oh, I guess that theory was wrong. Which means that it's not enough to be able to do an experiment to show that a theory is right and that the predictions are correct. The predictions must also be, Karl Popper used the word risky. In other words, scientific theory has to be able to make a prediction that could be shown to be wrong. A scientific theory that explains everything is actually no good. It has to be possible to do an experiment to disprove the scientific theory. Okay, this is the demarcation criteria of falsification. Again, demarcation means how do we demarcate what is science from what is not science? And Popper's answer is science is falsifiable. Here's a much simpler statement of Popper's idea. Insofar as a statement speaks about reality, it must be falsifiable, and insofar as it is not falsifiable, it does not speak about reality, at least not scientifically. Now, by the way, there are other types of knowledge that are not scientific knowledge. This is not to say that every true statement has to be falsifiable. It's that every scientific statement has to be falsifiable. That's an important distinction. So this idea, I think, gets folded in with the scientific methodology. Popper says that for a theory to be scientific, it has to be able to make predictions, and it has to be possible for those predictions to turn out wrong. Otherwise, the theory can't be meaningfully tested. This gets somewhat twisted post-Popper to suggest that what scientists are doing when they do an experiment is they are attempting to falsify their theory. That's nonsense. Scientific theories are the end product of the scientific endeavor. You don't want your theory to be wrong. If your theory is wrong, it means everything you and your colleagues have been doing for the past 50 years is wrong. Scientists aren't trying to falsify their theories. They're trying to verify the predictions. But it has to be true that it is possible that those predictions turn out wrong. Otherwise, what you're doing is not science. So I think this idea that scientists are always looking to toss out their scientific theories for something new and better is it's a slightly twisted version of what Popper was saying. Popper wasn't telling you how to do science. He was telling us what science is. But this does mean something important, which is that you can always show a scientific theory to be false, but you can never be 100% sure, there should be a percent sign there, 100% sure that a scientific theory is true. Okay? So scientific theories can be disproven, but they can never be proven. The fact that scientific theories can't be proven per se is a result of the kind of logic we use in science. The kind of science we use, the kind of logical reasoning we use in science is inductive reason, not deductive reasoning. Deductive reasoning is a kind of reasoning based on postulates and logical conclusions drawn from those postulates. This is the kind of reasoning we use in mathematics. You have a postulate or an axiom, and then you prove a bunch of theorems from that axiom, and you arrive at a conclusion. And if your logic is sound, the truth of the conclusion is guaranteed by the form of the deductive logic. Okay, so this is the kind of logic that you use in a mathematical proof. It's the kind of logic that Sherlock Holmes uses to find out who the killer was. Deductive logic. Inductive logic is based on observations. You make observation after observation after observation, measurement after measurement after measurement, and then you make a generalization from those observations. Inductive reasoning is by its very nature open-ended, because the number of potential observations you can make of the world is infinite. That means the generalizations that we draw from those observations are always temporary. For example, suppose I wanted to go out and look at birds, and I went out and I looked at a bunch of birds and I looked at a bunch of crows, and I made observations of 100 crows, 1,000 crows, 100,000 crows. And every crow I take a picture of in my field exploration of birds is black. From this, I can draw the inductive conclusion, the inductive generalization, all crows are black. That's a perfectly reasonable inductive generalization based on those hundreds and hundreds of observations. Except, all it takes is one observation of a crow that is not black, and you have to throw away, or at least modify, your generalization. Okay, so one scientific fact or observation is enough to falsify an inductive generalization. All crows are not black. Most crows are black, except crows that suffer from some sort of albinism or pigmentation mutation. So crows are mostly black, except for those with genetic mutations. Okay? I can still draw a generalization, but that generalization has been modified by further experiment. This means that because scientific conclusions are inductive, that they're always temporary, and that scientific truths are always provisional. Science is by its very nature open-ended and subject to change. This is a strength of science and not a weakness of science. If you open up an astronomy textbook from 20 years ago, you will find the Big Bang theory in there. You will find something saying the age of the universe is 15 billion years. If you open up the astronomy textbook that you're using this semester, you will find 13.64 billion years. Does that mean science is wrong? No, it means science is by its nature constantly changing. And as our measurements get better and better, our numbers in our textbook will change. Nobody expects that the science textbook that you are using right now for astronomy or for physics will look exactly the same in 25 or 40 or 50 or 100 years. Okay? Because the science textbooks we use today do not look the same as those from 20 or 40 or 50 years ago. Science changes gradually, and it also occasionally changes abruptly. This is the last idea I want to talk about, and then we'll wrap up this video. There's a word that gets tossed around when talking about how scientific theories change that can be, again, abused and used in a way that's a little bit imprecise. And I like to make sure we use this word only when it's warranted. And that's the idea of a paradigm shift. You have probably heard this term before, a paradigm shift, indicating a big change in thinking about something, usually science. The application of this word to science comes courtesy of another philosopher and historian and historiographer of science named Thomas Kuhn, again, early 20th century philosopher of science, historian of science, who wrote his most important work, The Structure of Scientific Revolutions, in 1962. Probably the most influential work in the history and philosophy of science ever. Doesn't mean everything in it's right. Doesn't mean there aren't a lot of philosophers who very much disagree with a lot of what Thomas Kuhn said. But if you corner a physicist and ask them to name a philosopher of science, they will probably say Thomas Kuhn. His ideas are very influential, especially among scientists. It's worth mentioning that Thomas Kuhn did have a degree in physics. He wasn't just a philosopher. And Kuhn coined this word paradigm to talk about how scientific systems of thought change. And that doesn't just mean how we come up with new scientific theories and how old scientific theories get disproven. A scientific paradigm, according to the way Kuhn uses the word, is bigger than a theory. A paradigm encompasses not just the ideas of a field and the current laws and facts and theories, but it encompasses what are the tools and techniques used by a field. What are the rules of inquiry and the definitions of terms? What do words mean? And what is the scope of what's considered a legitimate question to ask about the world? A paradigm encompasses not just what our current theories are, but the questions of what is science allowed to ask questions about? What questions are open to scientific investigation? And so when a paradigm shift happens, it's more than just we throw away an old theory and we have a new theory. It completely changes the questions we can ask about nature in a way that's bigger than just tossing out one equation for another equation. So a paradigm shift is by its very nature incredibly rare. These are once a century things that happen in the history of science. What are some examples of paradigm shifts that are relevant to our course? The shift from a geocentric universe where the Earth is at the center to a heliocentric universe where everything goes around the sun was a paradigm shift. How do we know it's a paradigm shift and not just a new theory? For example, the word planet means something different in the geocentric model and the heliocentric model. The Earth was not a planet in the geocentric model. The Earth was the center of the universe and the place where we live. The Earth is a planet in the heliocentric model of Copernicus and others. So we can ask questions about the motion of the Earth, which would not have been questions before, because our whole picture of the meaning of planetary motion had changed. In the early 20th century, we discovered that there are other galaxies, that our own Milky Way that we see as a stripe across the sky is not the whole universe. It is one galaxy, and there are hundreds of billions of other galaxies. So we could start asking questions about the size and shape of the Milky Way galaxy and its distance to other galaxies that would not have made sense before we knew that there were other galaxies. The Big Bang model of the history of the universe was a paradigm shift in cosmology. We could suddenly ask questions like, how old is the universe? That would not have been sensible questions before we knew that in the past the universe had come from this small, dense state. Before the Big Bang model, everybody, at least physicists and astronomers and cosmologists anyway, thought the universe had kind of always been here and had kind of always looked the same as it does now. And certainly there was no way to answer the question, how old is the universe, in 1890. But in 1924, now that we know that the universe is expanding and in the past had to all be in one place, now we can answer a question like, how old is the universe? So these sorts of paradigm shifts are essential for the progress of science, and they are big and disruptive. It's not as simple as, oh, I guess today we use this equation instead of using the other equation. They change the scope of scientific inquiry in a way that is drastic. Are we on the edge of another paradigm shift in cosmology and astronomy and physics? I don't think so. But one of the things that Kuhn points out, and I've taught classes where we used Kuhn's book as a text, where we read through it and discussed a chapter every day. I actually really, really like this book and could talk about it a lot, and we don't have time in this course or a course like this to do that. But one of the things that Kuhn points out about paradigm shifts is you don't really know you're in one when you're in one. That paradigm shifts are only visible in retrospect. After the paradigm shift has happened, you can look back and say, oh, this picture is completely changed. We have to throw out all of our own vocabulary, all of our old definitions, all of our old approaches to knowledge, because they don't work anymore. And Kuhn points out that it's impossible to do science without a paradigm, without something to guide what questions you are asking about nature. So we can't ever be in between them. That change has to happen all at once. And it's really fascinating to read Kuhn's take on how that happens, even if you don't 100% buy it. And I admit that I don't 100% buy everything Kuhn says about how science works, but it's a fascinating read anyway, and it's a way of thinking about science that I think is really, really important. Okay? So that is all I will say about science as a process. Although over the course of the class, I will come back to some of these definitions and some of these terms as examples of how scientific theories unify things, how evidence has guided the development of our modern theories of astronomy and cosmology, because it's that relationship between evidence, the facts and laws that we derive from experience and observation and measurement, and the conceptual theories that we construct around them. That process is science. And I don't really care much if you memorize how many moons Jupiter and Saturn have. But I do care a lot that you understand how it is that we arrived at our modern picture of the scale of the universe and the age of the universe and how the universe has changed over time.